Alright, so I'm just going to do a real quick talk about Lewis dot structures. Lewis dot structures are a way of writing, it's a symbol for an atom showing its valence electrons. Now, valence electrons are the electrons in the outermost energy level. So the two examples I have here are carbon and oxygen. Carbon, if we did the electron configuration, you can see that in the highest energy level, the outermost energy level, it has 4 electrons. They're both in the 2 energy level. That's the highest energy level. So we have to show all 4 of those electrons. To do that, you kind of imagine like a fake box around the outside of the atom, and you're going to put electrons along that box, and you can only put 1 electron on each side before you start doubling up, and you can put a maximum of 2 on each side. That would give you a total of 8, and we know that a full outer shell is 8 electrons, and so that would be happy. So with carbon, we have to put 4. So you start, I usually start on that side. You don't necessarily have to, but it works. And then you put 1 on each side, and you're good to go. Now on oxygen, oxygen has 6 valence electrons, and so you would do the same thing as with carbon, but then you would double up like that. And notice here, carbon has 4 single electrons. The single electrons are the ones that are going to want to bond. Well, carbon always makes 4 bonds. Huh, look at that. Oxygen, how many bonds does it make? Typically 2. So it's kind of cool when you see it come together. So if we were to go up the periodic table, you'd have hydrogen, then helium. We'll come back. Lithium, then, you have a new outermost energy level, so it only has 1. So if you notice, everything in the same family is going to have the same dot structure. So hydrogen, lithium, sodium, potassium, so on and so forth, they're all going to have the same dot structure. Then moving over after, you just keep going. If you went to column number 2, let's look at magnesium. Magnesium is going to be similar to helium, even though helium's a noble gas. It's got 2 just like magnesium does. Calcium also has 2. If we went over to something like boron, boron now has 3, so you would go like this. Alright, aluminum also has 3, so you do something like that. We did carbon. Well, silicon would be like carbon. It would have 4. Nitrogen has 5, so if you were going to do nitrogen, you would do 1, 2, 3, 4, 5, and nitrogen mostly makes 3 bonds, so that works well. Phosphorus would be the same way. 1, 2, 3, 4, 5. So you keep doing this until you finally would get to like the halogens. So fluorine, you put 7, it's left with just 1. That's how the halogens look. Neon, that would be your noble gas, and it would be totally full. So if we wanted to move on and look at how this would work in drawing like bonding, showing bonding diagrams using Lewis dot structures, what you would do, let's take an example like hydrochloric acid. You got hydrogen and chlorine, that would make HCl. Well, hydrogen structure is this. Chlorine is a halogen. So, oops, I did that out of order. Better not do that. You go 1, 1, 1, 1, 1, 1, like that. Well, notice they both have 2 bonding electrons, 2 that are single and ready to mingle. And what you do is just connect them. A line represents 2 electrons that are shared. If you had something like methane, methane is CH4. Carbon has 4 electrons, and each hydrogen has 1. So look how that works. Just match up the bonding electrons, and you should be good to go. You'll get something that looks like, well, if I can get it to go, that should be hydrogen, 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 and hydrogen. Sorry, that's a little messy. But essentially all you're doing is just matching things up and putting them together. This also helps explain the diatomic elements, the elements that always exist in pairs, because you get something like hydrogen. Hydrogen always comes in pairs, okay? Nitrogen always comes in pairs, oxygen, it's Brinkelhoff, okay? Well, hydrogen each has one. Well, look, it's perfect to bond. Nitrogen, they each have 3. So look, perfect to bond. So you would end up with that. It's kind of nice. So hopefully that